All right, so in this chapter, we are going to be doing vector calculus, and so you have to dig back and remember what it was to have a vector and things like that. So anyway, we're going to have something called a vector field. So if you watch the, there's a video link that I put in today's folder that has kind of like a guy doing an introduction to what vector fields are. But basically a vector field is just, you know, when you have an object that's like moving or whatever, then when you have a vector field, at every single coordinate, every single xy coordinate or xyz coordinate, a vector field defines like what's happening there. Like if you are drawing a vector field and let's say when you plug the point 1, 1 into the problem, you know, the vector goes off like that. Then you plug in 1, 2 and it like points up a little bit more, and then maybe it goes like this. So the vector field tells you like what's going on at that point, like which direction you're moving. It gives you a vector for the direction that you move. So like example like this one. So in 2D, here's a vector field and it's not even defined for what it is, but it's just like, oh, hey, when you're here, you move there. When you're here, you go there. Here, you go there. So it would almost be like telling you, like when you pass through that point, the equation, the field is going to like push you a certain way. Okay, so that's all you need to understand for now. And actually, I'll just kind of jump ahead. There are some vector fields, like this is a picture from your book. This is a vector field showing you San Francisco Bay wind patterns. And so when the little arrows, they do have like different like lengths to them, but what has been done here is they're all made the same length, and instead they're used color to like denote the strength of that, because when you have a vector field, each little line here, like maybe this line here is like super long, so that indicates like a strong push that way, versus these are like only like slighter pushes. Okay, so the length of the vector is the strength of that motion. All right, and so this is probably indicating color, like, you know, the wind patterns, like maybe, you know, red is very strong, yellow is not so strong, white is kind of weak, so they start to do that. And then here's some other vector fields. This is the ocean currents off of the coast of Nova Scotia. So it does look like they left like the length in there because these are really little and these get longer, so stronger currents. And then this is airflow past an inclined airfoil. So anyway, you can see that basically the air goes past it, but you know, it's changing a little bit here. So there's something in the way there, and so it's going around it. Anyway, so let's go back to where we were. So what you're going to be doing is at the beginning here, you're going to have to graph the vector fields. And so you're going to be given like an equation, all right? You're going to be, this is a vector field, right? And so you can write it like this with the I and the J. Remember, I hat is the direct, what you're doing in the X direction, and J is what you're doing in the Y direction. And if we had 3D, we'd have a K. But remember, you can also write this like this. You could put negative Y, comma, X. This could also be equal to f of x, y. Like somebody could write it like this. These are two different ways of writing it, okay? And so see what happens when I plug 1, 0 into this problem. So if I put 1, 0 into here, the 1 is the x, so that's going to go here, which in turn means it's there. And the 0 is the y, so it's 0 there. So you see it kind of flip-flop and does the opposite. So like, let's try a point like, you know, -2, -2. So you flip-flop because the x and y change places, and then this one's the opposite, so that's why this became +2. So all these points, if you plug them in, their x and the y value into this basically equation, it changes them to this vector. And so it tells you what happens at that point. So if I go to 1, 0, it's the vector 0, 1. So here's 1, 0. The vector 1, 0 is up 1 over nothing, so it's a little tiny arrow. And the magnitude of this thing, the magnitude of your vector function there is equal to 1, because the square root of 0 squared plus 1 squared. All right, so let's look here. 2, 2 makes -2, 2. So here I am at 2, 2. Then I have to go left 2, up 2. So that's that arrow right there. Okay, so that's that vector. So if you figure out the magnitude of this one, remember it's the square root. 2 squared is 4, 2 squared again is 4, so the square root of 8. So that's why this is longer there, because the magnitude of that vector, like the strength of what's going on there, is the square root of 8. Okay, and so you can just like see all the rest of that. Now, there is a site that is in a website, or a link to a site that is in Schoology that will graph these for you, so you can kind of check them. So I'm going to try to turn the camera upside down here and show you that. So if you go to that site, let's see, I'll put it upside down. So there, you can kind of see it. So if I type in this last one we were just doing, it was what, negative y, and then it was x. All right, so there it is. And you could kind of start to see that swirl as we were doing it, but this is a very, like, a lot more vectors going on here. Like they were doing vectors at decimal points and so forth. Okay, so kind of cool. So like a tornado pattern. So you can use that link to kind of like check your answers and stuff too, if you want. It's kind of cool. All right, so we are going on. So basically this is just about how you can do all of this in 3D as well. And so, but there is a link to like a 3D vector field grapher in there in Schoology. But to do these by hand, that would be really hard, because like it's just too hard to imagine and to draw in 3D. So you know, you would have 3 functions right there instead of 2, and you have I, J, K, and so basically we would just let computers do this, right, for us. So it's going to be too hard for us to do it in 3D, like on a piece of paper. So common physical examples of vector fields are velocity fields, gravitational fields, electric force fields, right? So velocity fields, that we're going to use that one in a second. So basically, if you have given a vector field, and you take the derivative of each part with respect to x and y and all that, you'll see in a minute, then you get the velocity vector, all right? And so we're talking about that in a second. So velocity fields are used to describe motion of a system of particles in the plane or space. And also velocity fields are also determined by flows of liquids, like fluid mechanics or air currents, which is aerodynamics. So they use those quite a bit. So if you're going to study one of those things. All right, so we already went over those pictures and whatnot. So we're going to work with fields independent of time. They're called steady vector fields. So a function f that assigns a number to each position in space is called a scalar field. And so that would be something like, say, there's a certain temperature at each point. So a scalar field is when you are assigning a number, you're not assigning something like x or y. Like you're not... like the thing that we were doing earlier, like negative y comma x, that would not be a scalar field because these have functions there. So a scalar field would be like putting numbers here instead of like variables. All right, so sketching a vector field. So this one right here, I'm going to skip over this, but if you sketch this vector field right here, this is my vector field, 2x comma y. Okay, it ends up looking like that, and I'm going to tell you something about that in a minute, because we're going to go and do one ourselves on the next page and then come back to this. All right, so I want to do this one right here. So on your homework, you'll have to make like a little table for yourself, and we're just going to like pick some points. All right, so my vector field is kind of an easy one, x, y. So we're just going to pick some points, and then it's just going to stay the same. All right, so like the vector is kind of going to match the point. All right, so if I put the point 0, 0, I get the vector 0, 0. Oops, arrow. All right, if I put, we'll go and graph them in a second. If I put 1, 0, I'm going to do 0, 1. I'm going to do negative 1, 0, and 0, negative 1. So those all pretty much stay the same. 1, 0, 0, 1, negative 1, 0, because it's matching there, and 0, negative 1. So I need to go to the point 0, 0 and draw 0, 0. So that's just a dot, so that doesn't really do anything. So 1, 0 makes a vector 1, 0. So when I go to the point 1, 0, I have to start here and draw the vector 1, 0. So I have to go 1 unit this way and up or down nothing. When I go to 0, 1, I have to draw the vector 0, 1. So here's 0, 1. I have to draw the vector 0 left and right and 1 up. So there's that. And so basically what's going to happen is this is going to be here, and this one's going to be here. Okay, so let's try some other numbers. Like let's try like 1, 1. Let's try like, how about 2, 0 and 2, 1. Let's try some of those. So basically, you know, that makes 1, 1. It's just up to you which ones you try. And this one's pretty easy. So I think after I do some of these, I'll just start like thinking of them over here. So let's see, 1, 1. So here's 1, 1. So when I'm at 1, 1, I have to go over 1, up 1. So it puts me right there. Okay. When I'm at 2, 0, here's 2, 0. I have to go 2 and then up nothing, up or down nothing. So that makes that vector here. All right. And so then how about 2, 1? Oh, that's where I was. So 2, 1 means I go from here, I go 2, 1. So I go like that. All right. So as I get further out, it gets longer. All right. So like if I go to 3, 1, I have to go 1, 2, 3, 1. So it kind of like goes like that. All right. If I go negative 1, 1, then I would go negative 1, 1. If I go negative 2, 1, then I go from here, negative 2, 1. And I could kind of like copy that one over there. All right, this one would be there. And so you can see it's like everything is coming out, right? And so once you get just a little bit of an idea of it, so I'm going to show you it on here. That would be X and Y. So here's a picture of it on the grapher. All right, so that's what it would kind of look like there. Everything's just like coming out of the origin, basically. Okay, getting a little bit longer as it goes out. All right, so sometimes it's helpful to like look at the magnitude, like to do a little bit of something with the magnitude. So if I find the magnitude of this thing, so the magnitude of f right now, that would be the square root of x squared plus y squared. All right, so let's let this magnitude equal to like a constant, right? Equals the square root of x squared plus y squared. So I would get x squared plus y squared equals k squared. So if you notice, that's a circle. So that means that what happens here, like when the magnitudes are going to match in a circular pattern. So look at this. So do you notice a circle with radius 1 over here? You don't have to draw this, but the circle with radius 1, do you notice everything coming off of that circle has a radius of 1? And if you go up to 2, 2, 2, 2, and 2. So if you go to circle number 2, everything coming off that, we only drew this one, but look, that has a 2. It has a 2, 2, and it would have 2 here. So it has a length of 2. All right, and if I picked a point like a random point like right here, I would, basically get a vector that was 2 units long and, going off in the direction that it's supposed to go. Okay, so sometimes that's helpful. And so that's what this problem back here was doing, was trying to show you here, that if you take these two pieces and you set their, set k equal to, so k is just like a certain thing, a certain number, a constant for your magnitude, you get 2x squared plus y squared. So that would be like 4x squared plus y squared equals k squared. And so what you end up starting to get is you get these like ellipses, right? Because this 4 is here. So it's like x squared over 1/4, that would change to, and then plus y squared. So you get these ellipses if k was equal to 1 right here. So like this first one right here, you have an ellipse and it's going to 1/2 in the x direction, and it's going to 1 in the y direction. See, that's 1/2 and 1. Well, as k changes, then this 1/4 and this 1 over here change, but it just gets like more. And so that's why this follows like an elliptical shape, because the magnitude of the vector here, if you go and figure out what shape the magnitudes take, it's elliptical in nature. So you don't really have to know that, but sometimes if you're doing something by hand, it kind of helps to maybe look at that in a way. All right. But anyway, let's do this next one. So here, my vector field is going to be y comma 1. So when I graph this, the y value no matter what the original y value is, the vector is always going to have a 1 here because it's just not changing. So whatever, it's just going to be 1 all the time. All right, so let's do like 0, 0. So even 0, 0, this 0 would come up here, so it'd be 0, 1. So 0, 0 is 0, 1. Let's go over to 1, 0. So if I go over to 1, 0, my y value is going here, so that's 0, 0, 1. So basically I can kind of tell you now that anytime I'm along here, anytime I'm on, you know, some x value comma 0, it's going to turn into 0, 1. So these are all going to go up like that. So you can kind of sense a little pattern. So let's try something like this, like 0, 1. So 1 is going to come there, and that's going to be 1. So 0, 1 is going to go 1, 1. Well, if I go to 1, 1. So basically what's happening is that the x value is being ignored, right? And I'm going to get 1, 1. So everything here is also 1, 1. So everything along this line right here, when y is 1, is going to be 1, 1, 1, 1. So let's do like 0, negative 1. So I'm going to get negative 1, 1. If I do 1, negative 1, I'm also going to get negative 1, 1. If I do 2, negative 1, I'm going to get negative 1, 1. So anywhere along this line, I get a vector that goes left and up. So it goes like that. Okay. All right, and then if I go ahead and put that into my grapher here, let's see, y, comma 1. I'll show you what it looks like. But it's a much better picture, but this is what it looks like. Sorry, I have to turn my camera upside down. All right, so that's what it looks like. Okay, and which is, we have just like a rudimentary version of that. Okay, and so here's one in 3D. We're not going to do 3D, so I'm just going to go ahead and skip that there. All right, so we're on the home stretch here. So let's see, a gradient as a vector field. So if your function determines a scalar field and the function is differentiable, then del f is the gradient vector field. So basically what we're going to do is, to get del f, we're just going to do the derivative with respect to x of the I part, and then the derivative with respect to y of the y part, and the derivative with respect to z of the z part. Okay, so we're going to get, that's called our gradient vector field. Okay, so let's just read through this. This is going to be important to us later, not so much now, but a vector field f is called a conservative vector field if it is the gradient of some scalar function, right? So that is, if there exists a function such that you can do del f on that function, and in this situation, f is called the potential function. All right, so this is the definition that we're going to need later. So a conservative vector field is a vector field that comes from another one, that is the derivative of something else, that it's someone's del f, it's someone's derivative. So it means there existed something before it that you did the derivative of to get it. So that's called a conservative vector field. Okay, so many important vector fields like gravitational fields are called conservative. All right, and the origin of most of this terminology is from physics. All right, so last one here. Okay, so if I wanted to find the gradient vector field for this function right here, so basically we just find our two derivatives. Okay, so if I do fx right here, the derivative of tangent is secant squared, so secant squared, oopsie, of 3x minus 4y times the derivative of this with respect to x would be 3. And then fy would be secant squared 3x minus 4y times the derivative of this with respect to y would be negative 4. So if I write that as a vector, my del f is those two things. So 3 secant squared 3x minus 4y, comma, negative 4 secant squared 3x minus 4y. Okay, so, you know, nobody would ever make you graph that one. That's a little bit much. Okay, so if we're trying to do our gradient vector field here, so that means that del f is the derivative of this with respect to x would be 2x, and the derivative of this with respect to y would be, that'd be 2 times a half, so you get 1 and the negative, so negative 1y. Okay, all right. So you would basically just go through that those motions again of having, you know, some points right here, 1, 0, we'll do negative 1, 0, we'll do 0, negative 1, and we'll do 1, 0. All right, so I would have double the x, so 2x, and negative y, so that's still 0. So double the x, negative 2, oops, no x right there, sorry, and then 0. Double the x, that's still 0, but that's 1. And double the x, so that would be 2, and oh, I had that one. I guess I needed, oh, whatever, I'll just put it again. But what I really wanted was 0, 1. So 0, and then that would be negative 1. All right, so we'll just do these first few, then I'm going to show you on the thing here. So 0, 0 would still be 0, 0. 1, 0 would be 2, 0. So at 1, 0, I would start here and go 2 spaces to the right. At 0, 1, I'm sorry, at negative 1, 0, I'd go 2 spaces to the left. So there. Okay. At 0, negative 1 down here, I would do 0, 1. So that one is here and pointing up. Let's see, at 1, 0, we already did, 0, 1, 0, 1, I'm at 0, negative 1, so pointing down. So let's do a couple more. Let's do like 1, 1. So 1, 1 would be 2, negative 1. So here, I go over 2, down 1, so it'd be there. All right, so let's do 2, 2. So that would be, let's see, 4, negative 2. So if I was at 2, 2, I go 1, 2, 3, 4, down 2. No, I'm sorry, that was 2, 1. So this would be negative 1. So from here, I'd go 4, down 1. So it'd be like over there. Okay, so all these things, these point that way, these are going to go this way. From the bottom, let's do one of those, like how about negative 1, negative 1. So that would be negative 2, comma 1. So here, I go left 2, up 1. So it would go there. Okay, so basically, the inside is pointing in, the top is pointing that way, the bottom's like pointing this way. All right, so if I do that here, my vector field, let's see, 2x, so just to show you, and then negative y. All right, so this is what it ends up looking like. Okay, and like I said, we saw the beginnings of that here. All right, so the last little bit here is we have at time t equals 1. This example here, a particle is located at the position 1, 3. If it moves in a velocity field, this velocity field, find its approximate location at time equals 1.05. All right, so at time equals 1, I'm able to plug 1 into here. At t equals 1. The particle is at 1, 3. That's what I am told. Okay, and its velocity, f of 1, 3, so that would be this one right here. So if I put a 1 and a 3, I get 3 minus 2 is 1. And let's see, if I put 1 and 3 in here, I get 9 minus 10, so negative 1. Okay. So, you know the formula for distance is rate times time. I'm trying to find the approximate location at t equals 1.05. So, after 0.05 units of time, it's basically from here to here, the particle the change in location should be approximately, right, like 0.05 times your vector right there, f of 1, 3. All right, so because basically, you know, distance equals your rate times your time. Your rate, that's your velocity, and then your time is 0.05. So we're trying to see like how much it moved, because it's going in this direction right here. And we're starting at 1,3 and we're going in that direction. So we have 0.05 times F. So 0.05 times my F is F of 1,3, so that is 1, -1. So the amount that it changes in the X and the Y direction is 0.05 times each of these. So 0.05, because 1 times 0.05, and -1 times that, that'd be -0.05. So basically what we're saying is that when we were at 1,3, we're going to change by this much. So the new approximate point I would be at would be adding 1 plus 0.05, so 1.05, and be taking away 0.05 from 3, so it'd be 2.95. Okay, so that's just like a little physics problem there. All right, so there's your homework. These two pieces are matching only, so that would be kind of quick. And this is some drawing, and a couple of these are figuring out, just like we did up here, you know, doing the derivative, and I forget what 33 is, but it might be drawing the del F. Okay, all right, that's it. Bye-bye.